This is our AP FRQ review on topic 1, which is area and volume. So to begin, I'd like to just review our formulas that we have for area and volume and kind of just very quickly develop these formulas once more with you. It's been a little time since we've done this. So let's say that we have two functions. Let's say we have f of x, some generic curve here, and let's say we have g of x down here. There's our g of x. And let's say that we'd like to find the area between these two curves from x equals a to x equals b. We know that the integral gives the area under a curve. So if we want to know the area between these two curves, that area, we can say that the area is equal to the integral from a to b of f of x, which will give the entire area from f of x to the x-axis, minus g of x, because if we want just the area between the two curves, we want to subtract out the area of g of x. So f of x, this is always the top curve, and the g of x here for us, this was our bottom curve. So if I was just asking you how to find the area between two curves, you could tell me that the area is the integral of the top curve minus the bottom curve with respect to x. If our curves are not functions of x, if our curves are functions of y, so let's say we have f of y and g of y, and we want to find the area of these curves between y equals some number, let's call it c, and x equals some number, y equals another number, let's call it d. So the area between y equals c and y equals d, that area, instead of doing a top minus a bottom situation, we are going to need to do a right minus the left situation, because the integral with respect to y of f of y will give us the area from the curve to the y-axis. So this area will be the integral from c to d, these are y values, of the right curve minus the left curve with respect to y. So this will be the right minus the left. And note that the right and the left have to both be functions of y. So there has to be y's in those equations. Don't leave x's in those equations if you're doing a right minus left situation. Okay. So now let's take our curve. Let's take our region that we can find the area of. Say we have f and g again. And let's say it's bounded on the left by some value a and on the right by some value b. And now let's say that we have this region R, and let's say that that region is the base of some solid. It's the base of some solid, so R is the base of a solid, and each cross-section perpendicular to the x-axis is some shape. Maybe it's a square, maybe it's an equilateral triangle, maybe it's an isosceles right triangle, maybe it's a semicircle, but it's some shape. Let's just do an equilateral triangle. Okay, so we have this base, each cross-section perpendicular to the x-axis. So for instance, here is one cross-section perpendicular to the x-axis. Each cross-section perpendicular to the x-axis is an equilateral triangle. So this cross-section, the solid would be coming up out of the page, and that would be an equilateral triangle. It's hard to draw this in three dimensions, but there would be an equilateral triangle here coming up out of the page. So there would be that equilateral triangle, and right next to it would be another slice that would also be an equilateral triangle, and another slice, and so forth. And all of these slices, an infinite number of slices added up together, would give the area of each slice added together from x equals a to x equals b would give us the volume of this solid. So in general, our very most basic formula for volume is the integral from a to b of the area of each slice, of area of each cross-section with respect to x. Or, if we're going right and left, c to d, of the area as a function of y with respect to y. Those are our most basic formulas. And again, this, with respect to x, that would be the cross-sections are perpendicular to the x-axis. And with respect to y, perpendicular to the y-axis. So back to our specific problem. So we have this basic formula. So for us, the volume would be we're going with respect to x because we're perpendicular to the x-axis, so integral a to b. And it'll be the area of each equilateral triangle. The area of each equilateral triangle. So we need to know some expression for the area of an equilateral triangle. Well, that goes back to geometry, and we learned all of these when we were learning this the first time. But the area of an equilateral triangle is square root of 3 over 4 times a side squared. So we need an expression for a side in our situation. Well, a side, if I look at this lying on the region, a side goes from f of x to g of x. So a side for us is f of x minus g of x. So this will be, that length will be a side. And why f minus g? Why not g minus f? Because think of the y value here and the y value there. This y value is going to be greater than this y value. So of course you're going to subtract the top minus the bottom. You would never subtract the bottom minus the top. That would give you a negative distance here. So the area of an equilateral triangle for us is this, where s is f minus g. So our volume would be the integral from a to b of the square root of 3 over 4 times f of x minus g of x all squared dx. So that was for a cross-section of equilateral triangles. Let's quickly review our other areas. The area of a square is just s squared. We would just take our s and square it, put that in there. An area of an isosceles right triangle. If you recall, there were two of these. One of them had its leg on the base. So our s value would be the leg of the right triangle, and the other had the hypotenuse on the region. And the one with the hypotenuse was the smaller of the two, right? That would create a smaller triangle than if a leg was on the base. Leg on the base is our old 1/2 base times height, where base and height are the same, so 1/2 side squared. Hypotenuse on the base is half of that, so it's 1/4 side squared. And then we also had the area, the cross section would be a semicircle. If we have a semicircle, that formula, if you recall, we derived it back then, pi over 8 times s squared. And that would be if the diameter was on the base, on the region. The diameter is the base of the solid. Okay? All right, so that takes care of our cross sections. Now let's look at our volumes of rotation. So let me draw a little figure here. Let's get our f of x and g of x back up here to give us some kind of a region. So here's f of x, here's g of x, and let's bound it on the left and the right at a and b. Okay? So let's say that this is our region, and we're going to take that region and we're going to revolve it around some horizontal axis first. So I'm going to call that horizontal axis y equals, let's say, c. We're revolving it around y equals c. Okay? So if you think about that, this region is going to be revolved around. It's going to form an odd shape. It's going to have a hole in the middle, right? So we're revolving that around. I could try to draw that for you. Should I try to draw it for you? I guess I probably should try to draw it for you. So this is going to be revolved around that axis of revolution. So that's going to be revolved around like that. On the outside, I'm not going to be able to see it because it's behind in that solid figure. And then this is going to be revolved, the axis of revolution, like that. It's going to produce, the slice here will be kind of a washer, a circle with a hole in the middle. And then we're going to keep on going around till we get over here. Oh, I think I failed here, but anyway, something like that, So this will be looking like this, and this will be, oh goodness, looking like that, something. I kind of failed, but that's okay. Hopefully you get the idea of what this was about. So each cross section, we still have our same general formula for volume. We need the area, right? We need the area. So each cross section now is this washer, right? Where we have a large circle and a small circle cut out. So a big circle that we need, and then we need to cut out this small circle. But we're dealing with circular cross sections, and the area of a circle is pi r squared. So that's going to be our kind of go-to here, pi r squared. So I need two radii, okay? So I need the radius, my big radius, and I need my small radius. And I'm always going for my axis of revolution because that's the center of these circles, right? So my big radius for me will be my again, we're still going top minus bottom, f of x minus whatever this c value is. And then my little radius will be g of x minus that c value. And then we just put it in our volume formula here. So we have volume is equal to integral a to b. My big area will be pi times my big radius squared. That's my large circle, and then I'm going to subtract out my small circle. With respect to x. Okay, so remember, this was the area of the large circle. of large circle. I can't write today. And this was the area of the small circle that was a hole in our volume, in our solid figure. Okay. And you can factor out the pi and leave it outside, or you can just leave it inside. Either way is fine. We could, of course, do the same thing with respect to y, and sometimes we need to, but it would be the same thing, except everything would be in y's instead of x's. Okay? All right. Now, if you don't have it already, you need to go to our AP Classroom, go to our AP Review section, and then find your FRQ topic section and print off Topic 1, AP Review Topic 1. Print that off, and then come on back. I'm going to begin with number 2 from that worksheet. I'm going to leave number 1 for you to do. It's a good one for you to get started on. So the most recent test, AP test, that they had this topic on was from 2014 that I saw. They don't have it on here all the time. However, this year, who knows? Maybe it'll show up. We just don't know. Okay, I'm going to get a good color here. Try purple. Okay. In this problem, it was a no calculator, so we won't use a calculator. They say to let f of x be e to the 2x. Let R be the region in the first quadrant bounded by the graph of f, the coordinate axes, and the vertical line x equals k. The region R is shown in the figure on the right. So here is our f of x. Here it's bounded by the coordinate axes and the line x equals k over here. In part A, it says to write but do not evaluate an expression involving an integral that gives the perimeter of R. The perimeter of R. So we need the perimeter here. The straight lines are not going to be a problem, but we need an expression for this, the length of this curve, right? So we're going to have to remember what our equation is for the length of that curve. And the length of that curve, it involves an integral. We derived it using a bunch of little lines way back when we did that, but it's been a long time since we've done that. We used the Pythagorean theorem an infinite number of times here. That gave us that integral. Pythagorean theorem, so we have that square root. And under the square root, it's 1 plus, and here we need f prime squared. F prime squared. So f prime for us is 2e to the 2x, right? So we need f prime squared dx, and that gives us the length of that curve. Now, I didn't do the boundaries. We're going from x equals, since we're in x's, we need x boundaries. We're going from x is equal to 0 to x is equal to k. So 0 to k. So that gives us, that's the hard part, that gives us the length of that curve. This length is 1. This length is k. And this length is the y value here minus 0. So then the y value there is e to the 2k. And that gives us an expression involving an integral that gives the perimeter of the region R. Let's go to part B. The region R is rotated now about the x-axis to form a solid. Find the volume V of the solid in terms of K. So we are going to take our region and rotate it around the x-axis. Okay? So when we rotate it, It's going to give a kind of a horn-like shape, and there's not going to be a hole in the middle. The whole thing is going to be solid. So in this case, we won't have a small circle to subtract out. It'll just be the whole large circle. This radius, the big radius here, will be the top curve minus 0, right? Our top curve is f of x. You can call it f of x, you can call it e to the 2x. Since they named it for us, you can totally just use the name f of x. So our volume will be the integral from x is equal to 0 to x is equal to k of pi times r big R squared, pi times r big R squared. And since we actually have to find the volume and not just write the integral for the volume, I am going to go ahead and write what f of x is. So pi times the big radius squared, pi r squared, that's the area of a circle, so pi r squared dx. That's the integral for it, and now we have to, since they said to find the volume, can't just leave it like that. We have to go ahead and figure out what this integral is. So let's simplify a little bit. I am going to move that pi out. So we have integral from 0 to k, pi is outside. When I square this, I get, when you square an exponent to an exponent, you multiply the two exponents. This is equal to pi times, let's go ahead and find the antiderivative. The antiderivative of e to the 4x is 1/4 e to the 4x. We got real good at those antiderivatives when we did our biparts integrals. We're evaluating that from 0 to k. And now we put the k in. In fact, before I put the k in, I think I'm going to move that 1/4 outside, make it pi over 4. So we'll have e to the 4k minus e to the 0. That would be a safe stop spot. And of course we could make that e to the 0 is 1. And if you wanted to, you could distribute the pi over 4 through, but we don't need to do that. Okay, next up. It says the volume V found in part B changes as k changes. If dk dt is 1/3, determine dv dt when k is equal to 1/2. So all of a sudden, when I see this dk dt, dv dt, all of a sudden I find out I'm needing to do a related rates problem now. I have this equation for V that I found in the previous problem, and now I need to do a related rates problem using that equation. So let's write that down. Let's write down our equation for V again. There's my equation for V. And I know dk dt is 1/3, and so I need to find dv dt when k is 1/2. So I come over here. Remember, you always take the derivative before you plug in any numbers. So take the derivative first. Since I'm going to take the derivative here, I think I'm not going to do this, but when I distribute this through, it'll be pi over 4 times 1. That'll just be a constant back here. So when we take the derivative of that constant is going to be 0. So we have dv dt on the left. That's the derivative of v with respect to t. Now we take the derivative with respect to t of this side. So I should have written this here. We are taking, on both sides, we're taking the derivative with respect to t. Oh, just lost that blue. That's okay. The derivative with respect to t of both sides. Okay? So dv dt, and over here, the derivative of this with respect to t. So the derivative of e to the 4k is 4e to the 4k, and the 4 is going to reduce with this 4 here, and I'm going to be left with just pi e to the 4k dk dt. Don't forget that. Because we're taking the derivative with respect to t, we need that. Okay, we took the derivative. Now we're going to plug in numbers. So I need to tell AP what I'm doing. So I'm going to say when k equals 1/2, dv dt is equal to pi e to the 4 times 1/2 times 1/3. It's all numbers, so that's a safe stop spot. So I'm just going to leave it right like that. Let's take a look at how this was graded. In part A, they awarded, when they graded this, they awarded 1 point for f prime of x. So 1 point right here for f prime of x. 1 point for the integral. So the entire integral, and then 1 point for the answer, which would involve everything else. So this one part was worth 3 points. In part B, they awarded 1 point for the integrand. So the integrand is this part here, right? Specifically, since we could have taken the pi out, specifically it was this part. Okay, but the pi is included there. 1 point for the limits of integration, so 1 point for the 0 to k, and then 1 point for the antiderivative. That was this part right here, 1 point for that antiderivative, and then 1 point for the answer. So this part of the problem was worth 4 points. And lastly, in part C, they gave 1 point for applies the chain rule. Applies the chain rule. So the chain rule is writing that dk, taking the derivative of both sides, writing the dk dt. That's how they would give it the way I did. There's another way to do this problem, but that's the way I did it. That's where that point would be awarded for. And then 1 point for the answer. So that part was worth 2 points. Okay, next up, let's turn to number 4 and let's do number 4 together. Number 4 was way back in 2008, and on this problem it was number 1, so they allowed calculator use on it. So I'm going to grab my calculator. You guys can do the same. I'm clearing out everything that's in my calculator. Okay. So let's see. We have let region R be the region bounded by the graphs of y equals sine of pi x and y equals x cubed minus 4x. So which is which? Which is sine x, which is x cubed minus 4x? If you don't know that from looking at it, to me it's obvious that that top one would be the sine curve and the bottom would be the cubic. But if you're not sure about that, then stick it in your calculator since you have a calculator. But this is the y is equal to sine of pi x, and the bottom one would be the x cubed minus 4x equals y. So part A, find the area of R. Well, I love this. Find the area of R. This is something we can definitely do. It's just the integral of the top curve minus the bottom curve. So the area of R will be the integral from the leftmost x, which is 0, to the rightmost x, which is 2, of the top curve minus the bottom curve with respect to x. Okay, now we have to find that area, so I go to my calculator, and in my calculator, since I'm pretty sure I'm going to be using these two curves over and over again, I'm going to put sine of pi x, get that to where you can see it, sine of pi x in for y1, and x cubed minus 4x in for y2, and I take a second and look to make sure that I got those in right, because if not, every one of my answers is going to be wrong. Then I go to my home screen, Math 9, 0 to 2, and y1, remember the easiest way to get to all of our y's is the alpha, and then we want to get to this f4, alpha f4. There's y1 minus y2 with respect to x, and we get a nice neat little 4. So that area is 4 square units. Okay, part B. The horizontal line y equals -2 splits region R into two parts. Write but do not evaluate an integral expression for the area of the part of R that is below this horizontal line. So let's come over and let's draw this. At y equals -2, we have this line, right? And now we want to find this area below that. So, well, we want to write but do not evaluate the integral that gives that area. So this area, now, same thing, top minus bottom, but now we have on top is -2, and on the bottom is our x cubed minus 4x graph. So for this one, well, one of our challenges, though, is to find these intersection points. It's not that great of a challenge, but it is a little challenge. Let's go and find those intersection points. And I need to tell AP what I'm doing, right? Communication. So I need to say the y equals -2 and y equals x cubed minus 4x intersect at, okay, so back to my calculator. I'm going to turn off my sine graph for right now because I don't need it right now. And I'm going to put -2 in for y3, and I'm going to graph, and I'm using the numbers here for my window that they gave. It looks like they went from 0 to 2, but see how they have a little bit showing on the left? I like that too. So I'm going to go from like -0.25 to 2.25 on my x's, and I'm going to go from -3. Looks like they went a little bit beyond -3, so maybe -3.25 to 1.25 on my y's. So that's just my the two curves that I needed there. And so to find the intersection points, I can do second calc 5. Sorry, that was alpha. Second calc 5, and enter, enter, enter. So that leftmost intersection point is when x is 0.539, so I'm going to say that x equals 0.539, and I'll give it a ... for AP because it does go on and on. Now I don't want to go find the other intersection point yet, because if I do, I will lose this current intersection point and I won't be able to use it in my integral, right? So I'm going to, well, I say that, however, we only have to write but do not evaluate. So that's not a problem. So I can totally lose that intersection point. Okay, so I'm just going to go find the next one. Second calc 5 again. Go over a little closer and then do enter, enter, enter. And there's my other intersection point. And x equals 1.675 ... Okay. Now, since I'm writing but not evaluating, I think I'm going to call this x value A and this x value B, and that way I don't have to keep rewriting these numbers. Not that I would have to rewrite them much, just once, but that's okay. So my area is now, the area of what they ask for is going to be the integral from A to B, from what I called A and B, of the top is -2 minus the bottom. Make sure you put parentheses around there. Whoops. X cubed minus 4x with respect to x. And that's it. That's a safe stop, and I'm just leave it like that. So that is the area that I'm asked to give. On to part C. Back to region R. Region R is now the base of a solid. For this solid, each cross-section perpendicular to the x-axis, that's good, we get to keep our x's, is a square. Find the volume of that solid. So we're back to the whole of region R, and each cross-section is now a square, right? Coming up out of the screen, out of the page, it's a square, right? So I need the length of that. It's just the top curve minus the bottom curve. So each side of the square is going to be the top curve minus the bottom curve. Use parentheses. Yeah? And we need to find the volume. So let's see. The volume will be the integral of each area, right? Remember, the area is just side squared, so sine of pi x minus x cubed minus 4x squared dx. Now, since I named this s, I could have just put s squared, and that would have been fine as well. And we're taking that from x equals 0 to x equals 2, so this is 0 to 2. So since it says find, I'm going to actually find it, not just write the integral, right? So back to my calculator. Get that focused. Okay, I have math 9, 0 to 2. And I'm squaring this, so parentheses y1 minus y2, close parentheses, square with respect to x. And I get 9.978 rounded to 3 decimal places. And that's it. Okay. All right, next up, it says the region R models the surface of a small pond. At all points in R, at a distance x from the y-axis, the depth of the water is given by this. So this is the depth of the water. Find the volume of water in this pond. Okay? Find the volume of water. Well, go back to your basic volume equation. Volume is always integral of the area with respect to x, or area of y with respect to y. So we have this as our general formula. I know the depth of the water at any spot, x units away from the y-axis, so at this distance from the x-axis, the depth is 3 minus x, right? The length is top minus bottom, and the depth of that is 3 minus x. So they've given me a little rectangle here, actually. This is just a little rectangle. The area of each of these little rectangles. So the length of the rectangle will be our sine of pi x minus our x cubed minus 4x. That's the length. And the width, or the depth, will be our 3 minus x. So our area is just length times the depth. So the volume will be the integral from 0 to 2 still of that length minus that depth with respect to x. So we'll put that into our calculator carefully, right? So math 9, 0 to 2 again. Okay, parentheses, sine x is my y1, minus the cubic is my y2. I'm going to close those parentheses and then subtract parentheses 3 minus x. Close that parentheses. With respect to x. And I'm thinking I did something wrong because that doesn't look quite right. What did I do wrong here? Oh, I see exactly what I did wrong. It's not a minus in here, it's a times, right? We're multiplying the length times the width, right? You multiply those. So I'm going to come in here. Thank goodness I made that little mistake. Make that just a times. It's going to work out much better. That looks better. So the volume here is 8.36995, right? So maybe round that to 370. Okay, let's take a look at how they graded this. In part A, they gave 1 point for your limits, which is just your 0 to 2. 1 point for your limits, 1 point for the integrand, and 1 point for your answer. So just that little area of R was worth 3 points. It's really good. Okay, in part B, they had 1 point for the limits. I understand that because we had to go find those intersection points. And then 1 point for the answer. So everything else. So that was worth 2 points. In part C, they gave 1 point for the integrand. Definitely the meat of this problem. And then 1 point for the answer. Total of 2 points for that part. And for the last one, 1 point for the integrand and 1 point for the answer. Total of 2 points. That's how they scored that one. Okay, I'd like to do one more with you. I'd like to do number 6 with you. Number 6? Yeah, I guess that's what I said, number 6. So let's do that one. I looked at these before I started the video. Let's take a look at number 6. This was from back in 2001. It was another calculator one. These can be no calculator or calculator. Just flip of the coin, you just don't know. Okay. So we have this, let's see, let R be the shaded region bounded by the graph of natural log x and x minus 2. Well, now I know which one is this. The curvy one is the natural log of x, and the line is the line. So in our calculator, I'm going to go ahead and put those in. So in for y1, I'm going to clear this out. And in for y1, let me wait for this to focus for us. There we go. In for y1, I'm putting natural log x. In for y2, I'm putting x minus 2. Okay. Part A, find the area of R. Area of R, nice. Well, we know it's top minus bottom, but we need to go find these intersection points. So tell AP what we're doing, right? So I'm going to say y equals ln x and y equals x minus 2 intersect at. Okay. Let's see, what's a good window for this? I have, I'm not sure what the good window for this is. I don't think it's going to be just too much. Let's just do zoom 4. It's going to do zoom 4. And that's all right. That's all right with me. I can find those two intersection points pretty well. So second calc 5, enter, enter, enter. And I get x is equal to 0.158 dot dot dot. I'm going to let that be a, and I believe I am going to need to go store that in for a this time because I know I'm going to be needing that. I wish it would not go unfocused here when I do anything with this calculator. All right, so I'm going to go store that in for a. So I'm going to go to my home screen. Right now, that this value is stored in for x, so I'm going to store that in for a so I don't lose it. Okay, back to my graph. Second calc 5, let's go find our other intersection point. Enter, enter, enter. And x is equal to 3.146 dot dot dot, and I'm going to go store that in for b. Second quit, and then x, store in for b, and now I'll always have those two, which should be crucial throughout this problem. All right. All right, so let's see. Find just the area. So the area of R will equal the integral from a to b of the top curve minus the bottom curve. So ln of x minus x minus 2 dx. And that will be, for us, Math 9, a to b of ln x is my y1 minus the line is my y2 with respect to x, and I get 1.949. 1.949. Remember, 3 decimal places at least. You can always give more. Okay. Part B. Find the volume of the solid generated when R is rotated about the horizontal line y equals -3. Y equals -3. When y equals -3, when I found this, -3 is way down here, right? So it is well below our region. So -3 is down here. We're revolving this region about that line, yeah? Going about that line. So it's going to be a thin little solid, right? With a big hole in the middle. So I need my outer radius that I need to keep, and my inner radius that I'm going to subtract out. So my outer radius will be, I think I'm going to come down here and say this. My outer radius is, I'm going to call it a capital R, is going to be my ln of x minus a -3, which is +3. My inner radius that I will be subtracting out, I'm going to call it little r, and that's going to be my x minus 2, again, minus a -3. So you can call it x plus 1 if you want. Okay? So I need the volume will be the integral from a to b still of pi times my big R squared minus pi times my little r squared. Right? Since I named it these letters, I can go ahead and keep it that. If you want to, for clarity's sake, you can put that in there if you want to, but really we don't have to. This is ln x plus 3 squared minus pi times x plus 1 squared dx. And now actually find, so we need to go ahead and get a decimal. So back to my calculator, and I go math 9, a to b again, of pi times ln x minus, or plus 3, minus pi times that x plus 1 squared. I forgot to, now that tells me I forgot to square this other one. Did I square my other ones? Yeah, I did. So I'm going to square that. I'm going to insert, hopefully I can do this. Yep, it worked. Okay. So pi r squared, don't forget to square. Okay. See if this looks right. 34.19. I'm going to round that last one to a 9. Okay. All right, part C. Write but do not evaluate. Write but do not evaluate. An integral expression that can be used to find the volume of the solid generated when r is rotated about the y-axis. So now we're going to take this guy and we're going to go around this y-axis. Well, there are two ways to do this. We can do the disc and washer method that we refreshed ourselves on, or you can do the cylindrical shell method. I think I'm going to do this in both ways. First, I'm going to do the disc and washer method, and then I'm going to remind you on the cylindrical shell method. So if we're doing the disc and washer method, we're going to need to go right minus left, and that's going to be my big R. And this is going to be my little r, right? But since we're going right minus left, we need to get all y's, right? We need to get all y's. It's not going to be just too hard here. I have y is equal to ln x. I need to solve that for x, right? So I just take e to both sides. E to both sides, and I get x is equal to e to the y. That was not that hard. And then for my line, I have y is equal to x minus 2. Solve that for x. X will be y plus 2. Not that hard. So my outer radius this time will be my it's the line, so it's the y plus 2, it's the line, minus 0, right? So just y plus 2. And the inner radius will be the curve, right? The curve minus 0, so e to the y. And so my volume will be the integral from c to d. Oh boy, we did not get the y values when we found those intersection points, did we? That's unfortunate, but we can go and do it now. So I will say that the y equals ln x and y equals x minus 2 intersect at y equals and y equals. I'm going to go find those real quick. So back to my graph, second calc, intersect. I'm already up there at that one. Enter, enter, enter. There was the x value. Let's just go grab that y value. So 1.146. 1.146. I'm putting that here because I know that's the higher of the two values. Dot, dot, dot. Okay. And then I'm going to go save that. And since it's the higher of the values, I'm going to save that in for D. It's the higher of the two y's. That didn't solve. That did not do that. That solved that. I did answer in for D instead of y in for D. So y, the current y value, I want to store that in for D. There it is. Great. And now back to my graph. Second calc 5. go get this other y value. It's the lower y value. Enter, enter, enter. And there's my lower y value. So negative 1.841, and that is stored in for y, so I'm going to go grab that. Alpha y, store that in for c, and so now I have c and d. And I think I'm going to say that this is c and this is d. Let that be c and let that be d. Now I can use that. So the volume will be from c to d of pi times my outer radius squared minus pi times my inner radius squared with respect to y. Back to my calculator. Oh, we had to write but do not evaluate. So we're done with that. We don't need to evaluate. So we're good. So that is the disc and washer method. Let me refresh you on doing this the cylindrical shell method. In the cylindrical shell method, I've already kind of butchered up this drawing up here, so I'm going to redraw it real quick here. There's our curve, there's our line, and we're revolving this around the y-axis. So we're going around this y-axis. For cylindrical shell, you get to keep taking vertical slices, and you're creating the shell, right? Creating that shell. And the area of a cylinder, the area of that outer part of that cylinder, is 2 pi rh. H is the height, r is the distance from your axis of revolution to that slice, right? Which is always, here it's always that x value. So r is x, and h is the height, which was our natural log x, minus our line, x minus 2. So the volume will be the integral, and since we're all in x's, we get to keep those x values. You get to keep the a and the b. A and b, 2 pi r h. And that's it, and we're done. We didn't have to go find c and d. We didn't have to solve for x. We just used that formula and we're done. Let's look at how these were graded. Okay, in part A, they gave 1 point for the integrand. 1 point for the integrand. 1 point for your limits. And 1 point for the answer. So that was worth 3 points. So 1 point for the integrand. Do not forget your dx, you guys. 1 point for your limits, finding those boundaries, and 1 point for the answer. In part B, they gave 2 points for the integrand. I don't know if they split that up into the two pieces. I don't know, but they gave 2 points for the integrand. And they gave 1 point for the limits, the constant, and the answer. That's how they did it that time. 3 points total. So 2 points for this integrand. 1 point for the limits. The constant is the pi, okay, and the answer. And then in part C, they gave 2 points for the integrand and 1 point for the limits and constant, for a total of 3 points. Okay, so 1 point or 2 points for the integrand, whichever way you did it, and 1 point for the limits and the constant. Limits and the constant. Okay, and that's that. So practice on your own. Do try your hand at the rest of these practice problems, these review problems. Check your answers against mine on our Google Classroom and bring me any questions that you have. And I think we're going to be spending 2 days on this, so we'll check in. We have a couple of days to go over these, so you'll be able to have time to do all of these problems. Students always ask me, Miss Murray, how many do we have to do? And my answer is, that depends on what grade you want to get on that AP exam. If you want to get a 5, I strongly suggest you do all of these, okay? And I don't know why you would take that AP exam if you're not shooting for a 5. So go ahead and do them all. We have 2 days. You're good. Okay, I'll see you guys on our Zoom session. Bye.